Good afternoon, everyone, and thanks for joining us tonight. We're starting 1 minute late. I apologize for the delay, but wanted to get things kicked off here. So our topic for the presentation tonight is increasing milk production per acre. And I have a number of different things that I want to speak about, so we're going to jump right into it. When we think about increasing milk production, there's a couple of different pieces that I want to talk about. The first piece is, what are the possibilities? What are the potentials? And what is the milk production potential and forage production potential that we really have? And the next piece I want to talk about is what are the management pieces that need to be put in place to achieve substantially higher yields and substantially higher quality. And then the third piece is, how do we actually do it? What are the specific pieces? What are the specific products that we can apply at what stages to get these results that we're talking about? So I believe that forages have this tremendous untapped potential, yield potential, and quality potential that we consistently fail to harvest and that we don't even usually think about as being possible. So some of you have, I'm sure in many prior conversations and presentations, I've talked about the tremendous untapped genetic potential of plants, where Charles Tsai back in the 70s published a number of different peer-reviewed papers in which he described the genetic potential of a corn plant to be 1,100 bushels per acre or greater. And we're today harvesting only a very small fraction of the genetic potential that the corn genetics of today are capable of. This is very well understood and agreed upon by many scientists and breeders and geneticists. So we can ask the question, why are we tapping only a very small amount of the inherent genetic potential for all these reproductive crops, such as corn and soybeans and tomatoes and so forth? But with forages, when we're producing alfalfa and grasses and sorghum, Sudan grass and so forth, we are not harvesting a reproductive crop. We're harvesting a vegetative crop before it has the chance to reproduce. So for these vegetative crops, we're not limited by the plant's genetic yield potential. We don't have those same limitations. The crop doesn't have those same limitations. So in reality, our only limitation is the speed at which that plant can photosynthesize and build plant biomass. And this is a number that we can influence very substantially. It's most plants, most crops that we work with and what we've come to accept as being common today are only photosynthesizing at 20 to 25% of their inherent photosynthetic potential. So that means if we can increase that number by 4 to 5 times, when we're working with a reproductive crop, such as a corn or a soybean plant or a tomato plant or a stone fruit tree, when we increase the sugar production and the photosynthesis by 4 times, that doesn't mean that we get a 4 times yield increase, because a lot of those sugars, only a portion of them are going to fruit. The rest is going to plant biomass and to root biomass and root exudates and so forth. But with these vegetative crops, there is a much bigger contribution, a much bigger proportion of that sugar increase actually goes to plant biomass. So we can easily talk about having a 100% yield increase or a 200% yield increase of these vegetative crops. So I want to talk a little bit about the possibilities, the potentials, and then how we can achieve and fulfill those. So I'd like to begin by asking the question of, how do you measure yields? And I believe that we need to look at yields with a broader metric, a more encompassing metric than simply tons of forage per acre or pounds of protein production per acre. I believe that if we're farming livestock, beef or dairy or whatever the case might be, we need to look at our ultimate final number and ask, what is our milk production per acre? Dairy farmers, for example, are used to thinking about dairy production or milk production in terms of milk production per cow. But I would suggest we need to take a bit of a broader framework and look at the entire farming operation and ask the questions of what is our total milk production per acre, and then balance that also with the quantity of feed that is imported onto the farm, because obviously milk production per acre is going to be different for different operations depending on how much feed that they import. But I believe this is a more encompassing number that can really, when we look at milk production per acre, that number has a more encompassing effect that can also take into consideration the forage quality and not just the forage tonnage and yield itself. So a question for you. If you were certain that you could harvest 4 times more forages per acre and that you could do so profitably, but that it would take more intense management and that you'd have to manage it much more closely than what you may be doing currently, would you do it? Would you be willing to make that additional investment and commitment in terms of time and energy, and in many cases money, to produce a substantially higher yield, knowing that that higher yield would make you a lot more money and that you would be more profitable than you are right now? It's a very important question. It's going to take more time and energy for certain as a farm manager. And I want to speak about some of those pieces that will be required. So if you knew for certain that you could harvest 500 bushels per acre of corn, or 6,000 pounds per acre of grass-fed beef, or 30,000 pounds per acre of 100% grass-fed milk, how much are you willing to commit to make that happen? Because these are not, these numbers may seem like fantasy numbers, but they're really not. They're not at all outside the realm of possibility or even probability. According to Don Huber, in 1972, in the early 1970s, he was working with a group of researchers scattered throughout the Midwest where they were routinely talking about producing 500 bushels per acre of corn, not on a test plot on one farm or another in scattered regions, but consistently on large-scale operations all across the Midwest. So what has happened? Today, farmers aspire to producing 300 bushel per acre corn, and only occasionally, with some groups of growers, does the conversation even come up about the possibilities of producing 500 bushel corn. We don't even consider that to be an achievable goal anymore, by and large. So we've actually gone backwards quite substantially in the last 40 years in our understanding of how to manage plants nutritionally and agronomically to achieve these exceptional results. In 1978, in an early issue of Acres USA, there was a front cover article about an Idaho consultant named C.J. Fenzow, who set out to demonstrate the tremendous yield production potential of forages and 100% grass-fed beef. So he rented 31 acres of land from a local farmer in Idaho, fenced all of the land into 1 acre paddocks, and set up an irrigation system so that he could sprinkle irrigate all of these 1 acre sections. Then this land, he put on applications of soil amendments, and in the fall he planted a combination, I remember reading this a long time ago, he planted a combination of brome grass and red clover, a lot of the older style genetics. This was before a lot of the new cool season grasses and the genetics that we have available today. The following May, he purchased 240 head of stockers, 600-pound stockers, and put them into a 1 acre paddock. He kept those 240 stockers in each of those 1 acre paddocks for 24 hours. And then at the end of the 24 hours, he rotated them to the next paddock. And immediately when the livestock were gone, he sprinkle irrigated that 1 acre paddock and watered in all the manure and all the nutrients that the livestock had left behind. By the beginning and the middle of June, the those 240 stockers could no longer consume all the forages that were being produced by those 31 acres. So he tightened up his rotation to a 20-day rotation, and he stayed at a 20-day rotation for the duration of the growing season. And that fall, he sold those 240 stockers that had mostly been finished on those 20 acres. So he calculated that with the exception of a few weeks at the beginning, those 240 stocker cattle on 20 acres, he produced 6,000 pounds of 100% grass-fed beef per acre. And this 6,000 pounds per acre is not, this was not on the hoof, live weight, or not even carcass weight. This was finished boned meat per acre. So this is tremendous yield potential that we have failed to tap into and have failed to consider as being possible. So what I'd like to explore and talk about is what were Don Huber and Charles Tsai and their colleagues doing to produce 500 bushel per acre corn? What was unique about CJ Fensow in producing 6,000 pounds of grass-fed beef per acre? What can we learn from their examples and adapt to our operations today to produce these same levels of performance? So another example, this is a farm that I worked with in central Pennsylvania, or Lancaster County, Pennsylvania in 2010, an Amish farmer who put on foliar applications. He'd done a history of a lot of soil amendments and so forth. And he started experimenting with foliar applications applied 7 days after each cutting. And typically we have this idea that the first cutting is the heaviest cutting of the year. And then from that point forward, every cutting produces fewer and fewer tonnage, less and less tonnage. And we get slight increases, in some cases, substantial improvements in quality over the course of the year. So, however, that wasn't the case with Henry. What he observed, these numbers are numbers in terms of small square bales per acre. So these are small squares, treated versus untreated with foliar sprays. The first cutting is about the same, 85 and 87, but then you can see this substantial divergence where the section that was treated with foliar applications increased in yield. Every single cutting after the first, every single cutting was higher than the first cutting, including the fourth and the fifth cutting. So this is a demonstration of, this was 100% pure alfalfa. This was not an alfalfa grass mix. This was pure alfalfa. So this is a demonstration of increased yield over the course of the season. So I haven't done the math on the cumulative yield of what this would have been for the entire year, but just scanning the numbers very quickly in round numbers, it looks like it's almost double, almost a 100% yield increase. So that's a really substantial increase, and this is another example that really got me started thinking of what really is the yield potential of forages and how far can we push it and what can we really achieve. Here's an example of a farm that we work with in central Pennsylvania. We started working with this farm in 2012. Alvin Peachy is a young farmer who purchased a farm in 2011. And so he purchased this farm in 2011 and started using AEA foliar products in 2012. He was using our foliar applications as well as Rejuvenate and Spectrum for soil applications. And he saw his, over that period, you see his yield numbers or his feed costs dropped. His cow numbers increased from 35 all the way up to 58. His replacement heifer numbers substantially increased from a low of 8 all the way up to a 35. And milk production per acre, when he started using foliar applications, jumped from 4,400 to 7,000 to 8,000 pounds per acre. So when you take those numbers in combination, you think about the fact that his cow numbers almost doubled from 35 to 58. His heifer numbers more than doubled. And his feed costs went down, his imported feed costs. Those were feed costs per cow, by the way. And his milk production per acre increased from that 4,000 4,400 level to about, it stayed right around 8,000 pounds per acre for the last 4 years of that period through 2016. Oh, and by the way, in 2016 was Albin's first year as a 100% grass-fed dairy. So absolutely no grain. And his milk production numbers per acre stayed exactly the same. So he was still producing 8,000 pounds of milk per acre, even with no grain input. And part of the reason for that success is, of course, when we have a 100% grass-fed operation, one of the main challenges is energy. We don't have a problem growing protein. We can grow more protein than we know what to do with. The challenge is keeping enough energy for the cows. And to produce that high level of energy, we need to have forages that have a really high fat content. So one of the, what we look for on a forage analysis is a forage that has a fat content greater than 4%. Once it gets up above 5%, then really fun things start happening. Cows start doing really well, and the reproductive systems are working very well. So as an illustration, this is a diagram that we've developed to describe the gradual evolution that we see in plant health, where plants become healthier and more resistant to different types of diseases and different types of insects based on the stage of physiological development and what is happening and what's going on inside the plant. So I have an entire other presentation that I've done on the plant health pyramid. You can find that information. I'm not going to review this in depth, but what I would like to review very quickly, the first two levels. Level 1 is when we have really good photosynthesis and plants have high levels of complete carbohydrates and low levels of soluble sugars in the plant sap. Level 2 is when plants have high levels of complete protein and low levels of nitrates and ammonium and urea in the plant sap. So those first two levels are purely a function of chemistry. You can achieve on forages and on many crops, you can shift plants to have complete carbohydrates and complete proteins very quickly with a foliar spray of the right nutrients. So those, and you can do this in a hydroponic system as well. So these first two levels are comparatively easy and straightforward to achieve on a large field scale. But level 3 is where we need to be at level 3 if we want to produce high fat content forages. So level 3 is when we have increased concentrations and production of lipids inside the plant. And to achieve that, to get to level 3, we need to have really active, really intense biological digestive systems in the soil profile. This is a bacterial process, a biological process, not a chemistry process. And this is very important to understand, that if we really want to get high energy forages and increase milk production per acre, we have to have really good biological systems in the soil profile. You can't do this purely based on chemistry and with fertilizer inputs. So before I move on and jump on to some of these other pieces that I want to talk about, if you have any questions, I know I'm moving through a bunch of information fairly quickly. If you have any questions at any point, down at the bottom of your screen, you see a Q&A box, and ask any questions that you have. I'm alone here on the webinar. We don't have a moderator. So as I jump through this, once I get to the end of the presentation, I'm going to look at all the questions that you've put in and go through those and answer all the questions that you've asked. All right, so getting to level 3, having really aggressive biological digestive systems. How do we do that, and what happens when we are successful in that? So when we talk about producing double the forage yields, producing high fat content forages, 6,000 pounds of beef per acre, 500 bushels of corn per acre, how do you do that? How do you get those results, and how do you make that happen? So the key, this, I'm sure in many agronomy conversations, many people talk, many teachers speak about photosynthesis and how important photosynthesis is. We may almost think as that it's an old topic and it doesn't need to be rehashed. But what I've experienced for myself personally is that we talk about photosynthesis, but it's this abstract idea that we don't really understand how to manage. So we don't understand how to influence photosynthesis in the field very clearly. And this is the piece that I want to talk about. So all of you, I'm sure, have quite a good understanding of what photosynthesis is. Plants absorb water from the soil, which is H2O. They absorb carbon dioxide from the air, which is CO2. And through the catalytic energy of sunlight and chlorophyll, they combine CO2 and H2O, carbon dioxide and water, to make this simple sugar molecule called glucose, which is C6H12O6. And the extra oxygen, there is additional oxygen left over from that process, and that oxygen is released into the air. So if you were to look at this process, instead of looking at this picture and diagram, if you were to look at this as a mathematical calculation, you might write it like this: carbon dioxide plus water multiplied by chlorophyll plus light equals photosynthate production, glucose production. That's really what we're talking about. So you look at these pieces, carbon dioxide, water, chlorophyll, light, and the question that we have to ask as farm managers is, which of these pieces can we influence? Which of these pieces can we make a difference on for the crop that we're growing? So what can we reshape and what can we do to have an impact? And really, it's three things. We can influence carbon dioxide, we can influence water, and we can influence chlorophyll. For the most part, unless we're growing indoors, we can't really have a substantial influence on light. So I'm not including that as a part of this conversation. So when we think about these three pieces, carbon dioxide, water, and chlorophyll, let's talk for just a moment about what each of these three pieces are and how we can manage them, how we can influence them. So carbon dioxide, just to set the background for a moment, give you a couple of reference points. One of the pieces that was studied during the 70s and 80s was the possibility of using dry ice as a source of carbon dioxide for cornfields during the summer months. So if you have a cornfield, if you have a corn plant that is photosynthesizing very well, then the air around us typically has somewhere in the vicinity of 300 parts per million carbon dioxide. And when you have a rapidly growing cornfield that is photosynthesizing very quickly, it can deplete 100%, I shouldn't say 100%, but 95% of the carbon dioxide in that air mass in the cornfield in a matter of 2 to 3 hours of sunlight in the early morning. So that means that for the rest of the day, that plant's photosynthesis is limited based on carbon dioxide availability. So actually for corn production and for many of these vegetative legumes and forages and so forth, carbon dioxide is in fact a very substantially limiting factor, and it's slowing down the overall potential and yield for that crop. So we know that when farmers used to, and some organic farmers still do, cultivate corn for weed control, there was this idea that when you cultivate corn, you get this very rapid growth response where you might get 4 to 6 inches flush of growth in a matter of 24 hours. That was always thought and considered to be a nitrogen response, but that was not a nitrogen response. That was simply a carbon dioxide response. When you cultivate the soil, you introduce oxygen into it, you get this flush of carbon dioxide availability from oxidation of organic matter. So that flush of carbon dioxide resulted in this very rapid plant growth. We do the same thing in the horticulture industry, in greenhouse production, if we're growing greenhouse tomatoes or cucumbers or so forth, where growers will maintain the carbon dioxide of the environment in the neighborhood of 11 to 1200 parts per million. So we're keeping carbon dioxide levels at levels that are 4 times higher than what they are in the field. And we know that this produces as much as double the plant biomass and overall plant vigor. So the question becomes, for us as farm managers, if it's not really practical for us to distribute to dry ice during the growing season, how can we increase carbon dioxide availability? And there's a couple of answers. The first, the long-term answer, the sustainable answer, is that we need to build a strong base of soil organic matter that is then released during the growing season. Because really, when you have organic matter, we talk about all the benefits of high organic matter content soils, of holding water and holding nutrients that might be soluble, such as nitrogen and phosphorus, and preventing them from flushing, increasing water holding capacity. Those are all valuable aspects and very important. But in addition to that, one of the fundamental and foundational reasons for having high organic matter content soils is so that we can release carbon dioxide during the growing period that plants can absorb and photosynthesize. We want organic matter to disappear. We want organic matter to oxidize during the growing season when there are plants that can harvest that carbon dioxide. It's at cross purposes to have crop residues such as corn residue and so forth that is oxidizing and disappearing in October and November. We don't want that to happen, because then we're losing that carbon dioxide forever. We want that carbon dioxide, or that carbon, those carbon reserves, to oxidize and release into the air as a gas during July and August, when we are trying to actively grow and fill a crop. So the key to releasing, to having a sustainable organic matter reserve and releasing that during the growing season when we most need it, is to make sure that we have very strong bacterial mineralization in the rhizosphere, in the root system. And that happens as a result of having good root exudates of sugars and enzymes and other photosynthates into the rhizosphere. So I want to talk in just a moment a bit more about how we can really trigger and drive bacterial mineralization and root exudates. So the second major piece that we can influence is water. So throughout much of the Midwest, particularly Illinois and East, and even Iowa, it's often, we don't usually consider irrigation as a necessity or economically viable for forage crops. And yet it can actually have a tremendous impact on yield, because think about it this way, very simply. You need water, H2O, as a part of the photosynthesis process to form glucose. When the water stops, the photosynthesis stops. Just like you've hit the off switch, just like flipping a switch, it's done. There is no more photosynthesis happening. So as you move further east to growers that we work with further east through Ohio and Pennsylvania, we often, it's very unusual for forage farmers, dairy or beef farmers or whatever the case might be, to irrigate their pastures and to irrigate their forages. But for those few that do, they're often experiencing anywhere from a low of 30 to as much as a 70% yield increase just from being able to irrigate their entire farm. So you stop to think about that. Let's say a 30 to a 50% yield increase for the sake of discussion. All of a sudden, the cost of a traveling sprinkler or an irrigation system becomes very affordable and very justifiable. Now, it's going to be more management intense. It's going to take more effort and more labor. It's going to require the need to develop a water resource, but it has the potential to really substantially increase your yield and production potential on your farming operation. So now let's talk about the third piece, chlorophyll. You can think of it this way. On every leaf, you have you have a certain number of square inches or square centimeters of leaf surface area per acre. That leaf surface area can only intercept so much sunlight and so many photons. That limit of how much it can intercept is based on the chlorophyll concentrations. And you can increase chlorophyll concentrations in every square inch or every centimeter of leaf area by a factor of about 4 to 5 times. So if you can produce a plant that has, or each leaf that has 4 times more chlorophyll, that means it's going to intercept 4 times more sunlight, and provided that it has adequate levels of water and carbon dioxide, you have the potential to produce 4 times more sugar, which then is going to be almost directly translated into total biomass production. So there are 5 nutrients that we have found that are a critical pieces for increasing the overall photosynthesis process. The first 4 that I've listed here directly contribute to increased chlorophyll concentrations and directly contribute to photosynthesis. So the first one, nitrogen, is obviously a part of the chlorophyll molecule. So chlorophyll, you have a single ion of magnesium surrounded by 4 nitrogens, is the heart of chlorophyll. So there we've addressed nitrogen and magnesium. If you look at iron, iron is the pipe wrench that puts chlorophyll together. It is not a part of chlorophyll, but it helps make chlorophyll. It is needed to create chlorophyll. So I find it intriguing. If you look at different industries use each of these 3 nutrients to make a plant really dark green. In agriculture, as in corn production, for example, we'll put on an application of nitrogen to make crops very dark green. If you go to the horticulture industry and flower production, they will often use magnesium and sometimes iron to make plants really lush dark green. If we look at the turf industry, turf also uses iron to make plants really dark green. So each of those 3 nutrients contributes increased chlorophyll concentrations, and when we combine all 3 of them, we make sure that plants have adequate levels of each of these 3 nutrients. We get tremendous increases in chlorophyll concentrations, very dark green plants, and plants that are photosynthesizing very well. The 4th element here on the list is manganese. So during the photosynthesis process, the plant is absorbing water, which is H2O, and the first step in photosynthesis is that water molecule has to get split into H2 and oxygen. So you separate the hydrogen and the oxygen. That process is called water hydrolysis. Manganese is needed for water hydrolysis. So this means that it doesn't matter how much carbon dioxide you have, it doesn't matter how much water you have, it doesn't matter how much chlorophyll you have, you can have all of these other pieces in place. But if manganese is low, you will not have good photosynthesis. Now, the interesting part, these last 2 elements, iron and manganese, when you conduct a tissue analysis or a forage analysis or a soil analysis, better than 90% of all the growers and the farmers that we work with across all of North America and parts of South America their soil analysis and their forage analysis will come back showing that they have high levels of iron and manganese, particularly iron. And yet the crop is iron deficient. How do we know that? We know that from a very practical, experiential perspective, that when we put on a foliar application of even very small amounts of iron, we get this tremendous crop response. So why is that? What's going on? The problem is that the iron and the manganese are both showing up in the forage analysis and on the soil analysis, but they are present in the oxidized form. For iron, that simply means the iron is present in the form of rust. It's oxidized, which means that it's not physiologically active. The plant cannot use rust. It can't use oxidized iron. It needs to have iron in the reduced form. And so what we're observing is we see tissue analysis or forage analysis reports that are showing that we have iron sometimes as high as 40, 90 parts per million, or even 200 to 400 parts per million. And yet the plants themselves, when we conduct a sap analysis that only measures the reduced iron, the reduced iron will come back 2 to 3 to 4 parts per million, usually under 5 parts per million. So there's substantial differences between the iron that shows up on a test and that which is physiologically active. So you may think that you have adequate levels of iron and manganese, and I can say with almost complete certainty that you do not. And you don't have to believe me. You don't have to take my word for it. Simply purchase an iron chelate and a manganese chelate that is in the reduced form, put on a foliar application, do a test strip, and see what happens. Let the plants tell you. You will see this dark green response usually happen very, very quickly. Then the fifth element on the list is phosphorus. And phosphorus is interesting in that phosphorus isn't actually directly a part of the photosynthesis process. So it's not necessarily needed for photosynthesis and increased sugar production, but it is needed to transfer this increased sugar production and move it into cells through ATP, adenosine triphosphate. And phosphorus is the energy transfer mechanism within the plant. So what happens, what are the symptoms of a phosphorus deficiency? When you look at a corn plant in the spring that's been planted into cold soil and you have poor phosphorus release, you see purpling of the leaves. That purpling of the leaves is the plant doesn't have enough phosphorus to convert all the sugars from photosynthesis, but it doesn't want to have an accumulation of soluble sugars in the plant sap, so it converts those sugars to anthocyanins. So anthocyanins are the same compounds that produce the purple color in blueberries. So you get this purpling expression on the leaves when you have a phosphorus deficiency. And the same thing can happen when you have, let's say we address these first four nutrients. The plant has adequate water, has adequate carbon dioxide, the sun is shining, and we add nitrogen, magnesium, iron, and manganese and make sure the plant has an adequate supply of those four nutrients. All of a sudden, sugar production quadruples. Now what happens with it? So when sugar production quadruples, the plant needs to metabolize and use a lot more photosynthates and a lot more sugars. And this is where we need phosphorus. So if phosphorus is in short supply, you can actually get purpling of the leaves from increased sugar production in July and August. We've seen this happening. It's a ton of fun because it's showing us that the plants are actually photosynthesizing very efficiently and very effectively. So this next piece that I want to speak to very quickly, and I want to be conscious of time. We're 40 minutes in already. So I'm going to move through this next piece very quickly. It's a very important piece, but I want to make sure that I'm able to answer your questions as well. So if we get this substantially increased forage production per acre, if we're able to produce twice the tonnage of alfalfa and a lot more forages, where are the nutrients going to come from? What about nutrient removal of calcium and potassium and so forth, as well as trace minerals? So I was asked to give a presentation on increasing nutrient absorption and how we can produce agronomic systems where plants actually absorb a much greater proportion of their nutrients from the reserves that are in the soil profile rather than us constantly adding them. So I wanted to speak to that piece specifically. So in the North American Midwest, average soils contain in the top 6 inches, this is just in the top 6 inches, they contain an average of about 40,000 pounds of potassium and 9,000 pounds of phosphorus per acre. So these are locked up mineral reserves that are a part of the soil mineral matrix. That these levels do typically not show up on a soil analysis. So the question becomes, how can we produce an agronomic ecosystem that allows plants to tap into these nutrient reserves? So I'd like to offer an example, a case study. This is a farm that we had been working with. This is central Pennsylvania. We've been working with Ruben Peachy for a couple of years. And Ruben purchased a new farm, moved over onto a new farm. And this new farm, there were several fields that were connected that made one continuous 40-acre field of 1-year-old alfalfa when he purchased it. So this 1-year-old alfalfa stand did not look really awesome. Wasn't looking so hot. Ruben pulled soil analysis, and the local distributor that he was working with made recommendations for a soil amendment application that included, they put together a combination, a pre-blended combination that included compost, limestone, rock phosphate, gypsum, and perhaps some K-mag as well. I'm not completely certain anymore. But as you can visualize, just based on that recommendation, the soil was very depleted. The mineral levels in the soil analysis were very low. So they put on this application that totaled about 2.5 tons per acre in total over the entire 40-acre field. Then Ruben split the 40-acre field into 3 sections. One section received no foliar applications. The second section received a single foliar application after the first cutting, 7 days after the first cutting. The second section received 2 foliar applications, one after the first cutting and one after the second cutting. So this photo is from a photo on this farm in the middle of August when I was there visiting. And these were photos from the third cutting itself. So you can see on the right where you have double foliars, you have substantially greater leaves. You have a different leaf shape, different leaf size. You have a much greater leaf to stem ratio than you do with the untreated control. So just for clarification, the untreated control on the left also had the soil amendment, but it did not have the foliar applications. So all 3 got the same soil amendment application. So the yield numbers for these 3 sections, this is just for the third cutting. The section with no foliar applications yielded a 3/4 ton per acre. The section with a single foliar yielded 1.25 tons per acre. And the section with a double foliar yielded 1.5 tons per acre. And when you look at these pictures, you can see that the section with 2 foliars has a much thicker stem, and that stem was also solid. It was filled all the way through with white pectins, whereas the no foliar control had a much narrower diameter stem, but it also had a hollow stem, which was really intriguing. So you think about this, you have these 2 sections. One has a 3/4 ton per acre, and with the control, and the full program has 1.5 tons per acre. That's 100% yield increase for just that cutting. So the field that has the section that has a 100% yield increase obviously has taken a lot more calcium and potassium and phosphorus and all of the sulfur and all these various nutrients from the soil profile as the control. So why did that happen? Where did it come from? In this particular instance, we can say that, well, it might have come from the soil amendments, which it's very possible that it might have. But the question is, why did the plant absorb it on a full program and not get the same response on the control? Why do we have these 2 very different responses? What was the sequence of events that allowed this to happen? So one of the pieces that we have observed on a number of different crops, corn, strawberries, and tomatoes, and forages, is that we can build soil organic matter while we are growing a crop. And we put together this diagram, which I called the biological cascade, to describe the process of what we see happening and what we see happening in soil profiles. So this is worth like the plant health pyramid of a much deeper conversation, which we'll have at some point. but I'm just going to give you a very rapid fire overview of what is happening here. So the first level, the first thing that happens is when you have plants that have full capacity photosynthesis. In other words, if typical plants are producing sugars at 20% of their inherent capacity, this means that these plants are at a minimum of 60% or greater. So they're producing a much larger volume of sugars in every 24-hour photoperiod. When that happens, they transmit a much larger volume of sugars out to the root system as root exudates, and that triggers bacterial digestion. So remember when I talked about glucose? Glucose is this simple sugar called C6H12O6. There is no calcium in sugar. There is no potassium, no zinc, no manganese, no phosphorus. There are no minerals in sugar. So when you have this bacterial population consuming sugars from root exudates, they need minerals to form their own cells and to form their own bodies. So they extract minerals from the soil mineral matrix. They can now tap into those 40,000 pounds of potassium in the top 6 inches and the 9,000 pounds of phosphorus in the top 6 inches and utilize those minerals to build their own cells and to build their own bodies. So then this bacterial digestive process is called mineralization, because as these bacteria are grazed upon by protozoa and nematodes and other organisms, the minerals contained within their bodies are now released into the soil environment in the form of organic acid and amino acid chelates. So now you have citric acid or an acetic acid chelate, carbonic acid chelate, where you have this weak chelation agent in that has attached to phosphorus or potassium or calcium or whatever the case might be in the soil profile. So these are now extremely available nutrients for the plants to absorb that prior were locked up in the soil mineral matrix. So now the next step is that plants begin absorbing these microbial metabolites. And when that happens, they become very energy efficient. They now have a surplus of energy. They have more energy than they know what to do with, because they no longer need to metabolize nitrate and ammonium and calcium and potassium ions. They're absorbing amino acid and organic acids, so they have much more energy. So when they have much more energy from microbial metabolite nutrition, they store that surplus energy in the form of lipids, in the form of fats and oils. This goes back to what I was discussing on the plant health pyramid when you get to level 3. So when you get to level 3 with this strong bacterial digestive process, you now, not only do you have a plant that has a high fat content and that has a lot of energy, but these high fat content plants also start transferring lipids and fats into the soil system. So when you begin transferring lipids into the soil system, you now trigger fungal digestion. Bacteria can't digest lipids. This is why historically in our culture, in the Amish culture that I grew up in, we used to preserve meat by storing it in fat, because bacteria can't digest fats. Bacteria, but fungi can. So now in the soil profile, this triggers fungal digestion, and we get a much stronger fungal population. And this fungal digestive process is at the foundation of what we call the humification process, in which we build really stable organic matter. So I need to keep moving. I'm spending more time on this than I anticipated, and I want to be considerate of your time and be able to answer your questions. So when you look at a plant's total sugar production over the course of its entire lifetime, that sugar production for a reproductive crop like corn or tomatoes or apples gets split into these 4 equal pieces. So from the moment a seed is planted until the crop is finally harvested, the total sugar production in one annual growing season is about 25% goes into plant biomass, 25% into fruit, 25% into root exudates, and 25% into root biomass. So, of course, this happens at different stages of the plant's life. If you're looking shortly after germination, when the plant is rapidly building frame, you're getting 50% or greater going into plant biomass, and the rest going into root biomass and root exudates. When you get to the framing stage or early growth stage, this can be split into thirds. When you get to the framing stage, where what we refer to as the framing stage is a plant. If we look at a corn plant as an example, a plant that is at about V5. So if you think about a plant that's V5, that's about 24 to 30 inches tall. It took the plant 6 weeks to get to that stage, depending on growth conditions, 4 to 6 weeks, let's say. In an equivalent amount of time, the next 4 to 6 weeks, that plant is going to grow from 30 inches tall to 9 feet tall. It builds a tremendous amount of biomass very, very quickly. But the interesting part is that during that framing stage, the majority of sugars don't actually go into plant biomass. They go out through the root systems as root exudates. In some cases, many cases, plants are actually contributing as much as 70 to 80% of their total photosynthate production in every 24-hour photo period out through the root system as root exudates at this stage of plant development. That's a tremendous amount of energy that a plant is investing into building a bacterial population in the root system. So this is really what we're feeding. We're feeding this tremendous bacterial population of soil profile. So this is actually a photomicrograph of what root exudates look like when they are coming off a growing root tip on a slide. If you look at this, this is actually a photomicrograph of a wheat root growing in solution. So if you look at towards the center, a little bit right of center of this photo, there's a bright yellow spot. And that is, you're looking at the root straight on. And all of the rest, this green film that you're looking at is really sugars that are leaving from the root system. And you can see all the bacteria and everything else that is growing in this system in the slide. So this is really what we want to create. We want to develop a rhizosphere that has a very aggressive bacterial digestive process. So then, of course, when you get to the reproductive stage, when you start building fruit and filling grain, now a lot of energy during tasseling and pollination, you start transferring energy into fruit. And then later on, during grain fill, the majority of the energy goes into the fruit. And very little goes into plant biomass and root biomass. So over the course of the plant's entire growth cycle, you get this total of 100% that is divided into these 4 equal pieces. But this only happens with full photosynthesis, with plants that are only photosynthesizing at greater than 60% of their inherent potential. This is what it can look like. This is what it normally looks like. So what it normally looks like is that you get much smaller total production of sugars, only 20% instead of 60%. And because you get a much smaller production, that plant is still going to work to reproduce. So a much larger percentage goes into fruit and a much larger percentage goes into root biomass, as much as 40-45% into root biomass or plant biomass, and as much as 30 to 35%, even 40% into fruit. So that means that roots, the root biomass and root exudates, get a much smaller quantity of sugars, maybe 35% of the total. So you have, if you were to actually convert this into the math of what these numbers would look like, with this plant, with this crop, you're producing, I'm just making up a hypothetical example. Let's say you're growing a crop that is producing 10,000 pounds of sugar per acre in plant biomass and fruit. That means you also have 10,000 pounds of sugars that are in the root system, in the soil system, in the form of root exudates and root biomass. With this plant, you only have a crop that is producing, let's say, 4,000 pounds of sugars per acre, of which 3,000 pounds are above the soil surface and only 1,000 pounds are below the soil surface. So the difference is, with this field, you have 5,000 pounds of sugars in the soil, and with this field, you have 1,000 pounds of sugar in the soil. So this is really understanding this piece and understanding photosynthesis and root exudates is really what drives bacterial action. So if we follow this all the way back to the example that I talked about at the beginning with Ruben Peachy and his alfalfa, he put on 2 foliar applications. Those foliar applications triggered a strong photosynthetic response that greatly increased the volume of sugar produced in every 24-hour photoperiod. That sugar went out through the root system as root exudates and produced bacterial digestion, which greatly increased the mineral availability from the soil amendments that he applied and from the soil mineral matrix. So we got this tremendous plant response and better nutrient absorption from a foliar application. This is why I am such a strong advocate of foliar applications, because I believe that they can be they're how we hack the system. With a foliar application, we can put on a few ounces or a few pounds of material or product per acre, and we can harness the photosynthetic engine to produce this tremendous plant response and improve the crop and also improve the soil. We can build soil health using foliar sprays far more economically than we can by using compost or using soil amendments. If you think about the math between these 2 examples and these 2 scenarios, if you think about 1,000 pounds of sugar per acre versus 5,000 pounds of sugar per acre here, and we can do all the conversions and look at moisture content and dry matter basis and what 1,000 versus 5,000 pounds of sugar can mean. We can do all of this math, but at the end of the day, you cannot economically afford to buy enough compost, to buy enough conditioned manure, to put on enough humic substances. You cannot compete economically putting on enough organic amendments on the soil profile to match what plants can do. You can put on foliar applications for 30, 40, 50 bucks, 120 bucks an acre for an entire season and produce a much greater response for the soil and for the crop than you can by putting on an equivalent application with compost or a soil amendment. So this is an example, just a very quick example. This is a farm in central Indiana with a single foliar application down. You can see the center line, darker green plants towards the right. And this is just an expression of plants that have higher chlorophyll concentrations and that are now photosynthesizing much better and producing a lot more sugars. So do you want to see the same results on your farm? What does it take and how do you do it? Really, you need to focus on feeding these. Feed bacteria in the soil profile. And to feed bacteria, you need to increase photosynthesis with your crop, with foliar sprays. So taking this down to a really practical application, focusing specifically on forages. You want to produce high-value alfalfa, high-value grass forages, pastures, whatever the case might be. What are the pieces that can have a substantial impact? First, for many soil geological profiles, we find a lot of value with an early spring application of gypsum, 200 to 500 pounds per acre. Why? Because you get a flush of calcium availability, you get a flush of magnesium availability, you get a flush of sulfur availability, and just nutrient availability in general. You get this substantial flush. And the sulfur and the magnesium are particularly important because in many cases with spring lush forages, you want to, when I say early spring, I'm talking about applying this on frozen ground before you get the spring lush. Because what you want to happen, the major challenge that we have with spring lush forages is that they are low in fiber and they are high in soluble nitrogen, urea and nitrates and so forth. So when we have high levels of magnesium and sulfur, it actually helps to quickly convert all of those soluble nitrogen sources in the plant to complete proteins. And our milk urea nitrogen and blood urea nitrogen levels can drop substantially, and we don't have cattle that have diarrhea from having excessive soluble protein in the diet. So it can be very valuable to increase the quality of the first cutting of forage and during the spring lush period. So that's an important soil amendment to keep in mind. Then additional really important applications is a fall application of Rejuvenate and Spectrum for similar reasons, but here we're focusing on a biological response rather than a chemistry response. So the gypsum application in the spring is a chemistry response which has a limited lifespan. It's going to last, depending on soil moisture and temperature conditions, anywhere from 60 to 90 days. And there are some residual long-term effects, but the greatest effect happens in the first 60 to 90 days. With a biological response, you don't get that upfront peak and then rapid drop-off. So we want to apply Rejuvenate and Spectrum in the fall. Rejuvenate is our biostimulant. Spectrum is an inoculant. And Spectrum, the bacteria that are in Spectrum this formula has been specifically designed to increase nitrogen availability and phosphorus availability from the soil profile. So they can tap into this soil mineral matrix and release nutrients. So when we put on this application in the fall, we get this accumulation over the winter months of available phosphorus, available potassium, available calcium, and this also helps the spring lush forages to be much higher quality. But in addition to that, we get this increased nutrient availability throughout the entire growing season. This doesn't have the drop-off effect that gypsum does. We still have strong nutrient availability in June, and July, and August when we are still growing a crop once the gypsum has started tapering off. So this application is very important from a long-term forage quality perspective, as well as the perspective of really building soil organic matter, as I was describing a moment ago with a biological cascade. The third important application is foliar applications. And these foliar applications we find for optimum performance to be applied roughly 7 days after grazing or cutting, when we have about 3 to 4 inches of regrowth. So when we have a small amount of regrowth, we have enough plant vegetative biomass to actually absorb the foliar application and to produce a nice response from it. And this is when we find to get the greatest economic impact. So if we're working with an alfalfa grower, they will typically put on 4 to 5 applications through the growing season. If they're in temperate climates, we've some growers that will put on as much as 6 or 7 if they have that many cuttings throughout the year. So the foliar applications, we tend to customize these based on forage analysis and sap analysis to apply specifically what that crop is looking for. But the two materials that we use probably 85+% of the time are Photomag, which contains the nutrients that are listed specifically to increase photosynthesis, and the forage foliar blend. So those two products put on as a foliar application 7 days after cutting or grazing are what are going to give you the biggest impact. So if you have any questions or want to, that we don't get to answer in this webinar, want to have a follow-up conversation with someone at AEA, you can contact one of these two guys, David Miller, Jason Stahl. They're both consultants on our team. David was one of the first consultants that started working with us probably 6 or 7 years ago now, perhaps longer. And Jason both come from an Amish background. Not that that's particularly important, but you can obviously tell that from their photos. So you can see their email addresses here and also the phone numbers. So I'm going to leave this slide up for just a moment, and I'm going to see what questions you guys have for me. And if you have questions that you've accumulated or saved up, now is the time to ask those. And you can type them in the little box down at the bottom of the screen. There's a Q&A box that you can look for. So one final thought that I would add to this, as you can tell, if you want, I believe it's possible to produce as much as 3 to 4 times higher forage yields than what we consider to be common or normal. I mean, we've heard stories about CJ Fenzau producing 6,000 pounds of beef per acre. I haven't tried to translate that into forage tonnage per acre, but I'm sure it's very substantial. So if this is possible, if these are the possibilities, I've tried to describe the various pieces that need to be in place in order to get that to happen. I think we need soils that have high levels of organic matter with strong bacterial digestion to release enough carbon dioxide. We need to have an adequate supply of water, and I believe that often means irrigation. And we need to use foliar sprays of nutrients to make sure that our plants have everything they need to photosynthesize well. And to do all of those things means that you will need to manage much more intensely than you may have managed up to this point. So I go back to the question that I asked at the beginning. If you were confident of these results, would you commit to the effort that it took to achieve those yields and to achieve those results? And by the way, all the farmers that we have worked with, whether they're producing alfalfa or they're a grass-fed dairy or a conventional dairy or whatever the case might be, these results can be achieved very, very profitably. There's a substantial ROI in putting on foliar applications at $120 per acre per year and doubling or increasing your forage production by 40 or 50% per acre. That's pretty substantial, particularly when you start measuring it in terms of milk production per acre instead of total tonnage per acre. All of a sudden, the yield numbers become really substantial and it becomes really economical. All right, so can I repeat what was in the foliar application? The two materials that we use are Photomag and a forage foliar blend. And the 5 nutrients that those two materials are specifically designed to address are, well, actually nitrogen is an outlier. We don't address nitrogen. We add that separately if it's needed, which it seldom is, but some cases it is. So aside from nitrogen, the 4 others that we address are magnesium, iron, manganese, and phosphorus. And if you have any additional questions on that, if you attended here at the webinar, you're going to be receiving a follow-up email with the slide deck. So you'll be able to look at the slide deck as well. All right, 2 more questions. Have we ever used these products on reclaimed strip mine ground? Such a fun scenario. The answer is yes, we have. Reclaimed strip mine ground is a lot of fun to work with, depending on your translation of fun. So the answer is yes, we have worked with these foliar applications and also with Rejuvenate and Spectrum. We believe the biological, because obviously with reclaimed strip mine ground, you have completely upset the native biology of that soil system, and you need to completely rebuild it. Not only do you just need to rebuild it, but you actually need to recover it from a negative situation. And so the applications of inoculants and microbial biostimulants, such as Rejuvenate and Spectrum, becomes more important, and it also becomes more impactful. This is where we see the biggest responses and the biggest changes happening, because it's very important to rebuild that biology in the soil profile. Great question. Greg asked the question, do we have any general recommendations for cover crops? And so this is actually an interesting question when we work with fruit and vegetable growers and so forth. This idea that we can build soil organic matter by growing a crop becomes particularly relevant for cover crops. So in fact, our most successful growers, and I should say the growers that we work with who are rebuilding soil very rapidly and who are making the most rapid advances on soil health, are the growers who treat their cover crop as if though it were a crop. They foliar feed their cover crops to make sure that they're photosynthesizing well. And they do this to make sure that they're producing the greatest amount of biomass and the greatest amount of sugar production in every 24-hour photo period. Lucy asked the question, is there any effect we should be aware of when livestock graze this improved photosynthesis area? Will they pace themselves correctly? So the effects are all going to be positive. Livestock, if you give livestock a choice, if you have a strip test where you've done a foliar application on one section but not on another, and you give them the opportunity to choose, assuming your foliar spray and your foliar feeding was designed correctly, they will always select the area that was foliar fed, and that forage will be higher quality. So being higher quality means a number of different things. It means that it will have a lower soluble nitrogen content. There'll be more complete proteins, which means that you'll have lower milk urea nitrogen, lower blood urea nitrogen. It will be more digestible, which means you should have a higher butterfat content. Depending on the forages, you may notice a protein content in the milk increase as well, although that's less consistent and less common. But we consistently see improvements in butterfat content. But in general, there aren't any negatives that you need to be aware of. They're not going to overgraze. You'll find that the forages will be much more filling. There will be fewer pounds of dry matter consumption because of the higher sugar content and the higher energy content. So in general, all the effects are going to be positive, and there's nothing really negative that you need to monitor for or be aware of. And as it happens, actually, this is something worth commenting on. When you produce these really high energy forages, problems with bloat on legumes disappear. It's something that we've observed on a number of farms. When you get calcium content and sugar content properly balanced and high enough in these forages, and you have a high fat content, we have farms that have grazed both with beef as well with dairy cows, stands that were almost pure clover with no negative side effects. And that's a really big deal, something that's very powerful. And then we have one question, Christina, is anyone doing this in the UK? I'm not. We don't do any work as a company. Advancing Eco Agriculture doesn't do any work in the UK at this point. I'm not aware that there are any farmers there that are foliar feeding. There may be, I don't know who they are. One more question. Van Slack asked the question, when you do a sap analysis on forage, is it species specific or combination, total sward? And same for trying to use a refractometer to measure Brix. So this is a great question, Van. You can do both. When we are doing a sap analysis, if there is one species that represents more than 70% of the total biomass, we will select just that one species. So let's say if we have an alfalfa grass blend, but 70% of it is alfalfa, we will measure the alfalfa and manage for the alfalfa. And the same would be true of a grass blend as well. If you have one species that has 70% of the total biomass, then we focus on really managing that species well. But if you have a truly diverse combination where you might have a dozen or more species that all represent relatively small percentages of the total mix, then I would just use the complete combination and measure and manage the entire combination, whether you're doing refractometer analysis or whether you're doing analysis in the laboratory, forage analysis or sap analysis and so forth. All right, I want to thank each one of you and all of you for being here for this webinar and for contributing your questions. I hope that you've found it useful and helpful. And if you have any follow-up questions, feel free to reach out to our team at AEA. And I look forward to talking with all of you again soon. Have a great day. Thanks, everyone. Bye.